My name is Rebecca Nealon. I'm from the University of Leicester, and today I'm talking about spiral, shadows, and precession in HD100453 as part of the 5 Years After HL Tower conference. This talk is part 2 of a 2-part series, so if you haven't yet seen part 1, please go ahead and do that. The link is in the description below. I'd also like to highlight and thank my collaborators that are shown here, as well as the institutes that have supported this research. So from part 1, we learnt that the protoplanetary disk HD100453 is a complicated system. It's described with an inner disk, an outer disk, and an outer companion. And in particular, we learnt that the outer companion has an orbit that is misaligned by 61 degrees to the outer disk. We quantified this by conducting a suite of numerical models that included both gas and dust, and used these to make synthetic observations which we could compare to the existing observations. In part 2 here, we're going to adopt the best fit orbit from part 1, which is shown in the graph in red, and use this to explain the other features that we observe in this particular disk. As a reminder, here's a sphere observation of HD100453. In the upper left corner, we can see the outer companion indicated by B, and in the lower right, we can see the primary star indicated by A, with its disk surrounding it and these two spiral arms forming structure in the disk. Now in this work we are interested in the unresolved inner disk that's around the primary star A and the orientation of this disk relative to the outer disk. First off, we note that there's a large gap between the location of the outer disk and the inferred position of the inner disk, and that strongly suggested that there's some kind of a companion, most likely a massive planet, residing in this gap. Now, although we can't resolve the inner disk itself, we do know it's there because of these narrow lane shadows that are cast onto the outer disk. The shape and relative position of these shadows tells us that the inner disk is misaligned to the outer disk by 72 degrees, making the inner disk and outer disk almost perpendicular to one another. So the question that we're asking in this work is, can this hidden planet that's residing somewhere in this gap be responsible for this strong relative misalignment between the inner disk and the outer disk? Or is there something more that's happening in this system? Our first step is to quantify the mass and location of this hidden planet. To do so, we conduct a suite of numerical simulations using the 3D hydrodynamic code Phantom. So here's a representation of our simulations where we consider 9 different combinations of planet masses and locations, with 5, 10, and 20 Jupiter masses shown down the page, located at either 10, 15, or 20 AU, shown across the page, with the planet shown as a white dot in each panel, and the yellow-green color representing the column density of the gas disk. Now, as we watch these disks evolve, interactions with the outer binary and the disk at periapsis cause these strong spiral arms to sweep through the disk, and these are explored in depth in part 1. In each of our different simulations, we see a big difference in where and how strongly the disk is truncated, particularly if we compare, say, the top left and bottom right cases. And so what we're looking for is a compromise between the inner edge of the disk being truncated close to where the observations suggest it should be truncated, which is shown by the purple circles in each of the panels, and some material being allowed to flow interior to the planet orbit to supply the inner disk, which we have not explicitly modeled here due to computational costs. We can simplify this representation with surface density profiles, which show the azimuthally averaged density as a function of the radius. And we had 9 different combinations on the previous slide, so here we have 9 different surface density profiles. In each panel, the small vertical line represents where the surface density is 10% of its maximum value, and the grey box represents our constraint from the observations. So what we're looking for are cases where the vertical line and the grey box coincide, which indicates that the inner edge in our simulated disk is consistent with the location of the inner edge as seen in the observations. From these results, we can see that if the planet is quite close to the star, so in the left column, for example, that the inner radius of the disk is too small. On the other hand, if the planet is more massive, so the bottom row, the planet accretes too much materials. It accretes too efficiently, and there's no material that can be used to supply the inner disk. So from this perspective, we'd say that the planet is located somewhere between 15 to 20 AU and has a mass in the region of 5 to 10 Jupiter masses. Okay, but a planet that's 5 to 10 Jupiter masses is quite massive, and it should be fairly easy for us to see in the observations. In particular, recent work by Christoph Pant shows that we can identify planets that are more than about 2 Jupiter masses through their kinematic signatures as they generate a deviation from the Keplerian velocity in the disk. So here we have the channel maps of HD100453 as observed by ALMA, and these channel maps show the regions of the disk that have the same velocity. Here the stars are indicated in cyan and the outer binary is close to periapsis. Now the structure that we see here is already not strictly Keplerian. If you recall from our simulations, we had these strong spiral arms that developed, and in the channel maps, these spiral arms are represented as these faint kinks that you can see just here. And these are discussed in depth in part 1, and we actually use these kinks to help us constrain the orbit of the outer companion. In any case, let's take a look at what we expect to see if there is indeed a massive planet hiding somewhere in this disk. So the observations in the top left and these 2 panels in the lower part represent our synthetic channel maps that we've generated using the radiative transfer code MC-FOST. On the left, we show the case of the 5 Jupiter mass planet at 20 AU, and on the right, we show the 10 Jupiter mass case at 20 AU as representative cases. Now, in the synthetic observations, the planet location is indicated with a cyan dot. First off, consistent with observations, we find strong evidence of the interaction with the outer companion, the spiral arms that are driven by this interaction. With these strong kinks driven by the spirals, it's actually quite hard to see the deviation that a planet may cause. So as an example, the left column middle row of the 5 Jupiter mass case shows a deviation at the location of the planet. But if you imagine that you didn't know the planet was there, the cyan dot was not actually there, it would be really difficult for us to conclusively identify this as a planet signature because of the mess that we have that's caused by the spirals. So this is a bit disappointing because it means that even if there is a planet hiding in these observations, it's going to be very difficult for us to identify it because of the mess that we have from the spirals. Okay, but what we could do instead is to take a look at this high velocity material. And so this is the gas that's closest to star A and is most likely forming the inner disk that we're actually interested in. We can see that while it's present in the 5 Jupiter mass case on the left, it's not really present in the 10 Jupiter mass case on the right. But this material is present in our observation in the top left corner, which suggests that a lower planet mass is more likely. So with this, and taking into account the assumptions that we made in the modelling, so for example, like our choice of the disk viscosity, we conclude that the planet is likely to be less than 5 Jupiter masses and located between 15 to 20 AU. Okay, so we're kind of almost at the complete picture of HD100. So on the right here, I've shown HD100453 schematically with all of its components. So starting from the outermost and working our way in, we have the outer companion shown with the blue star and indicated by OC, with its orbit indicated by the dashed ellipse. And then interior to that is the outer disk shown in blue. And from part 1, we know the relationship between the outer disk and the orbit of the outer companion. Inside of this, we have the inner companion indicated by IC and shown in green. And in this work, we've established that the inner companion has a mass less than 5 Jupiter masses and is somewhere between 15 to 20 AU. What we haven't done yet, though, is to explain how we get the relative misalignment between the inner disk and the outer disk. So the inner disk is shown in green, and if you recall, these two things are almost perpendicular, a relative misalignment of 72 degrees. So how can we generate such a strong misalignment with only the components that we see here? Well, in our paper, we explore a couple of mechanisms that may be responsible, but we conclude that the most likely option is differential precession. Simply put, the criteria for precession to occur is that the orbit of the companion is misaligned to the gas disk. This companion then exerts an external torque on the disk, and for these relatively radially narrow, wave-like disks, this results in solid body precession. In HD100453, the outer companion drives precession of the disks interior to it, so that's both the inner disk and the outer disk. Because they're disconnected by the planet, these disks precess effectively independently. In the top left corner, we have the formula to calculate how fast the disk should precess based on the properties of the binary shown in yellow and the properties of the disk shown in green. For the inner and outer disk, these properties are of course different. So if we evaluate this expression for both, we would find that they have different rates and that the outer disk actually precesses faster than the inner disk. Having these two disks precess differentially naturally leads to a relative misalignment over time, even if the disks start coplanar. And so as long as the disks are separated by the planet, which is indicated in the observations anyway, this misalignment is sustainable and can easily grow such that the disks are almost perpendicular. Okay, so our kind of more completed picture uses differential precession driven by the outer companion to explain the relative misalignment, as the outer disk precesses faster than the inner disk. But as suggested by the color scheme that I've used in the schematic, we can imagine HD100453 as a nested system. The inner companion and the inner disk are like a smaller, nested version of the outer companion and the outer disk. This means that ultimately the precession of the inner disk is driven mostly by the inner companion. Despite this, our analytic approach still suggests that the outer disk precesses fastest and faster than the inner disk. Now we call this configuration precession inception, where we have these levels of precession and nested precession. And as far as we know, HD100453 is the only protoplanetary disk that exhibits this kind of evolution, making HD100453 unique. Thank you for listening.